Welcome to Next Gen Manufacturing Nexus. Today we're diving into something pretty wild, a tiny invisible flaw that's holding back one of the most incredible materials on the planet, carbon fiber. Carbon fiber, it's basically a superstar material in the world of high-performance engineering. We're talking Formula One, cutting-edge jet fighters, you name it. It's crazy strong, ridiculously light. On paper, it sounds just about perfect. So what's the catch, right? If this stuff is so great, why don't we see it everywhere? Why is it still such a massive headache to make big, affordable parts out of it? Well, it all comes down to how you actually make the stuff.
All right, let's get into it. To really get what the problem is, we've got to look at the old school way of doing things. It's a process called autoclave curing.
So the easiest way to think about an autoclave is like a gigantic, high-tech pressure cooker. Seriously, you take all your sheets of carbon fiber, which are already soaked in this special resin, you lay them all up, seal the whole thing, and then this massive machine just cranks up the heat and pressure. It literally squeezes all the layers together to mash out any little flaws. And yeah, you get these super strong parts out of it, for sure, but the process? It's a huge bottleneck. These machines cost a fortune, they are painfully slow, and here's the real kicker. You can't build anything bigger than the inside of the pressure cooker. That's a serious limitation. Okay, so because of that exact bottleneck, the entire industry has been desperately searching for a better way. And that search has led to something called out-of-autoclave manufacturing, or just OAA for short. And check this out. The difference is just night and day. Instead of that giant, complicated, high-pressure machine, the OAA method just uses a vacuum bag in a regular old oven. Think about that. The promise here is huge. It's way cheaper, it's faster, and you can build parts that are practically any size you want. And this isn't just some lab experiment either. We're talking about organizations like NASA. They're looking at OA as the key to building these enormous, super lightweight parts for their next-gen rockets. The goal? To save a ton of money and a ton of weight. But, of course, there's a catch. There's always a catch, right? This amazing new method has a hidden enemy. A tiny, microscopic flaw that can totally wreck the whole point of using carbon fiber in the first place. So here's the deal. When you ditch that intense pressure from the autoclave, you create a new problem. Tiny little pockets of air and moisture can get stuck between the layers of carbon fiber. And these little pockets, these imperfections, they have a name: voids. And this image, wow, it just shows you the enemy perfectly. What you're looking at is a close-up, a microscopic slice of a carbon fiber part. See those dark spots? Those are the voids. You can think of them like tiny little cracks in the material's armor. They create weak points that, under pressure, could lead to a total failure. Not good. So how did engineers fix this? Let's get to the really clever part. The solution they came up with to fight these voids without having to go back to that crazy expensive autoclave. So here's the puzzle engineers had to solve. How do you let the trapped air out from between all those layers while at the same time making sure the gooey, sticky resin that holds everything together stays in? It's a tricky one. The answer is something called a semi-permeable membrane. And this is seriously cool. It's this super smart material that basically acts like a microscopic screen door. You put it on top of the carbon fiber inside the vacuum bag. The holes in it are big enough for tiny air molecules to escape, but they're way too small for the much bigger, gloopy resin molecules to get through. Brilliant, right? And you don't have to take my word for it. The data speaks for itself. This chart shows you the percentage of voids you get with the old method versus the new one with that special membrane. Look at that drop. It's a huge difference. It just proves that this smart screen door trick totally works. Okay, so we fixed a tiny, invisible problem. But why is this such a big deal? What's the macro impact here? It matters because by solving this one little microscopic issue, you basically unlock the entire potential of this new manufacturing method. This one tiny fix sends ripples through the whole aerospace industry. Suddenly, you can build lighter, stronger, and cheaper parts for everything, from the plane you fly on vacation to the rockets heading for deep space. And really, what you should take away from all this is that you've just seen next-gen manufacturing in a nutshell. This is how it works. It's this constant cycle. You find a problem, maybe a really subtle one, you engineer a super clever solution, and then you test the heck out of it to prove it actually works. And that relentless hunt for perfection, chasing down these invisible flaws to make our best tech even better,
That's what makes all this so cool. It really makes you wonder, doesn't it? What other tiny invisible problem are engineers tackling right now to build the future?